Bismillahirrahmanirrahim. In this video, I am going to be talking about chapter 3 of the book Islamic Science and Making of the European Renaissance by George Saliba. And this chapter is about the Muslim encounter with the Greek scientific tradition. So this chapter is about how the Muslims reacted to the Greek scientific tradition and how they corrected the mistakes of Greek scientists and how they built their inventions on it and added in new discoveries in it. So let's start. Cultural and political context. The translation of Greek and Sanskrit texts began in the late Umayyad and early Abbasid periods, driven by reforms initiated by Abdul Malik. Translators of these texts were initially viewed as outsiders, contrasting with those who aligned themselves with the Arabic language bureaucracy. Two primary groups emerged: foreign sciences specialists, often Greek and Persian speakers, and Arabic language masters, including religious scholars and bureaucrats who based their authority on Quranic and linguistic sciences. And this was because of the translation of the Divan into the Arabic language. So the Arabic language became the lingua franca of the Islamic civilization. Integration with Islamic sciences. Translators had to ensure that new ideas aligned with Islamic values, leading to the adaptation of disciplines like astronomy into fields such as Ilm al-Haya, Islamic astronomy distinct from astrology, and Miqat, a discipline addressing prayer times and other religious applications. The alignment of these sciences with religious needs allowed their proponents to ally with religious groups. Reaction to the Greek scientific legacy. Adoption of Greek sciences. Scientific texts like that of astronomy were accepted more readily than philosophical ones due to their objective correctness, avoiding theological conflicts. Errors in sciences, e.g., Ptolemy's miscalculations, had limited social consequences, unlike contentious philosophical ideas. Translation and corrections. Translators such as Al-Hajjaj bin Mattar corrected Greek errors driven by a competitive intellectual climate shaped by Abbasid reforms. Astronomical refinements. Early Islamic astronomers improved Greek calculations such as precession motion revised to 1 degree per 66 years from 1 degree per 100 years. Ecliptic inclination refined Ptolemy's value to 23-33 degrees. Solar apogee adjusted based on updated observations. Fusul method innovation. 9th century astronomers introduced the Fusul seasons method, refining solar declination observations and surpassing Ptolemy's flawed approach. Instrumental advances. Large sextants, e.g. Al-Khujandis, enabled precise measurements. 13th century innovations reduced observational points for accuracy. Subtler observations. Annular eclipses and solar disk size. Ptolemy's error. He claimed constant solar and lunar disk sizes, ignoring annular eclipses. Nasiruddin al-Tusi. He observed varying solar and lunar disk sizes, providing evidence for annular eclipses. Ibn al-Shatir calculated disk size variations and developed a new mathematical model to correct Ptolemy's errors. Lunar size variation. Ptolemy's model predicted impossible size variations at quadrature, with the moon appearing nearly twice its actual size. Ibn al-Shatir identified and corrected this flaw using eclipse observations, proposing an alternative lunar model. Critical approach to Greek texts. Islamic astronomers critically examined and refined nearly all parameters in the Almagest, produced observational treatises and verified tables Mumtahan to improve upon Greek astronomy. Constellations and star catalogs. Greek names were replaced with Arabic terms in translations. Two traditions emerged: Greek-based astronomical handbooks, Arabic practical utility-focused texts, e.g. for agriculture. Abdurrahman al-Sufi's contributions. He authored the book Suwar al-Kawakib as-Sabita, synthesizing Greek and Arabic traditions. He corrected Ptolemaic star descriptions and produced illustrated constellations with systematic tables. Broader impact. Islamic astronomers' critiques exemplified a rigorous and systematic approach to inherited knowledge. Their innovation integrated Greek and Arabic traditions, establishing an independent and advanced astronomical discipline. Mathematical construction of the Almagest. Mathematical advancements. Shift from codes to trigonometry. Tusi introduced sine, cosine, and tangent functions, replacing Ptolemy's code-based systems. He developed updated tools and tables for easier calculation in works like Tahrir al-Majisti. Integration and innovation. Early astronomers such as Habish al-Hasib blended Ptolemaic methods with contemporary advancements in new handbooks. Z. Textual revisions. Reconstructed the Almagest to simplify calculations and generalize methods for practical use. Streamlined planetary eccentricity models for clarity, as demonstrated in Tusi's Tahrir. Error identification and refinement. Corrected Ptolemaic errors such as annular eclipse oversight and precession rate inaccuracies. Improved observational techniques. Adapted methods like the Fusul for precise celestial measurements. Foundational critique and expansion. Treated the Almagest as a starting point for critical analysis and enhancement rather than an untouchable authority. Aligned foundational ideas with updated mathematical and observational insights. Cosmological problem of the Almagest. Inconsistencies with Aristotelian cosmology. Almagest contradicted Aristotle's principle of uniform circular motion around a fixed Earth. Ptolemy's mathematical models, e.g. epicycles, eccentric circles, were incompatible with Aristotelian physical realities. A circle moving on another circle is an epicycle, and eccentric circles are the circles that are not centered at the same point. Mathematical versus physical models. Ptolemy's planetary hypotheses treated celestial spheres as physical objects, yet introduced physically implausible scenarios, e.g. independent motion of concentric spheres. The celestial sphere is an imaginary sphere of which the observer is the center and on which all celestial objects are considered to lie. Spheres that share the same center are concentric spheres. Islamic critiques of Ptolemaic cosmology. Scholars like Muhammad bin Musa bin Shakir identified major flaws such as the implausibility of the ninth sphere. These critiques showcased deep mathematical and philosophical engagement with Greek science. Emergence of a new tradition. Ptolemaic inconsistencies prompted the development of an Islamic scientific tradition that integrated observation with cosmological coherence. Innovations addressed foundational issues with transcending Greek models. The astronomical Shukuk tradition. Early doubts and the birth of Shukuk. Initial skepticism about Ptolemaic astronomy emerged with Muhammad bin Musa bin Shakir. The former Shukuk genre began with Razi's critiques in medicine and philosophy, later applied to astronomy. Geographic spread and development. Andalusian works like Kitab al-Haya and critiques by Abu Ubaid al-Juzjani highlighted flaws in Ptolemaic models. Eastern scholars like Ibn Sina's students also contributed, showing widespread discontent. Key critique: the equant problem. Ptolemy's equant, requiring non-uniform motion around an off-center point, was deemed physically impossible. This issue resonated across astronomy and philosophy. Equant is an imaginary circle introduced with the purpose of reconciling the planetary movements with the hypothesis of uniform circular motion. Notable contributions: Al-Biruni criticized planetary latitude models and mechanical contrivances in astronomy. Ibn al-Haytham in Al-Shukuk ala Batlimos invalidated Ptolemy's lunar and equant models as physically untenable. Critique of Ptolemy's methodology. Ibn al-Haytham rejected Ptolemy's reliance on non-physical constructs like the equant, which contradicted the physical reality of celestial spheres. Stressed the need for mathematical model to align with observable physical truths. Principle of consistency. He emphasized the necessity for coherence between theoretical assumptions and the actual behavior of celestial bodies. He criticized the use of imaginary configuration lacking empirical or physical validity. Comparative analysis of Ptolemaic works highlighted increasing contradictions between Almagest and planetary hypotheses. Criticized Ptolemy's shift to slices of spheres, Manshurat, which introduced spatial and motion inconsistencies. Call for a new astronomy. Ibn al-Haytham advocated for a reformed approach to astronomy based on empirical observations and physically coherent models. He suggested Ptolemy failed to fully understand planetary configurations, necessitating a fresh framework. Influence on later thinkers. Ibn al-Haytham inspired scholars like Mu'ayyad al-Urdi to refine and challenge Ptolemaic astronomy further. He contributed to the evolution of Islamic astronomy by prompting a critical and innovative mindset. Nasiruddin al-Tusi, his early work Tahrir al-Majisti, provided initial critiques of Ptolemaic astronomy. Major contributions. His book Tazkira delved deeper into flaws in Ptolemy's lunar and planetary models. He critiqued the equant and the prosniosis slanting planetary axis, developed the Tusi couple, a mathematical model producing oscillatory motion from two circle motions, simplifying Ptolemy's complex configurations. He advocated for simpler, uniform circular motions over Ptolemy's convoluted planetary latitude models. Muhyiddin al-Akhawain died around 1500. He authored Al-Ishkalat fi Ilm al-Haya, Problems in the Science of Astronomy. He catalogued 7 major issues in Ptolemaic astronomy, including retrograde motion and uniform circular motion. He compiled critiques and solutions from earlier contemporary scholars, creating an anthology of challenges and remedies. Retrograde motion in astronomy is orbital or rotational motion of an object in the direction opposite the rotation of its primary or the central object. Later figures in the 16th century. Ghiyas ad-Din Mansur bin Muhammad al-Husayni offered solutions to Ptolemaic issues like uniform motion. Ghars al-Din Ahmad bin Khalid al-Halabi raised critiques of eccentrics in Ptolemaic astronomy. Ala ad-Din al-Kushji focused on specific problems rather than large-scale reconstruction. He tackled the Mercury equant problem, offering detailed solutions where al-Tusi had left issues unresolved. Shams ad-Din al-Khafri died around 1550. Renowned for combining critique with innovative constructions, produced some of the most sophisticated contributions in the tradition, blending analysis with new methodologies. Baha al-Din al-Amili died around 1622, did not directly address Ptolemaic problems but inspired followers who kept the tradition alive. Wider implications. Intellectual engagement. The persistent critique of Ptolemaic astronomy reflects a vibrant scholarly tradition that challenged and refined inherited knowledge. Innovation. Solutions like the Tusi couple and other refinements exemplify how Islamic astronomers contributed creative and practical advancements. Legacy. This dynamic tradition of critique and improvement laid the groundwork for subsequent developments in astronomy, influencing early modern European science. Theoretical objections. Methodological critiques. Mu'ayyad al-Urdi objected to Ptolemy's use of conjecture hads, which allowed speculative elements not strictly tied to observable evidence. Advocated for the validity of alternative models consistent with observations and cosmological principles, challenging the notion of Ptolemy's exclusivity. Interconnectedness of astronomy and philosophy. Islamic astronomers viewed astronomy as deeply intertwined with philosophical inquiries. They questioned not only the observational data but also the foundational cosmological assumptions, including whether constructs like epicycles and eccentrics were suitable for the celestial realm. Challenges to simplicity of celestial spheres. Ibn Shatir questioned the Aristotelian concept of celestial spheres made of a uniform divine element, ether, critiqued the inconsistencies like the sun emitting light while the rest of its sphere remained transparent. Alternative cosmological models. He proposed more complex models that departed from the strict simplicity dictated by Aristotelian cosmology, aligning better with observed phenomena. Reformulation of mathematical models. Ibn Shatir rejected models like eccentrics mathematics and developed alternative mathematical formulations consistent with observations. Shamsuddin al-Khafri advanced multiple mathematical models to explain the same phenomena, showcasing mathematics as a flexible language rather than a rigid framework. Impact on philosophy of science. Shift from Aristotelian frameworks. Islamic astronomers' critiques and alternative models gradually moved scientific discourse away from Aristotelian cosmology. This shift anticipated later Renaissance developments that questioned the Aristotelian worldview. Reconciliation of theory and reality. Their work emphasizing aligning mathematical models with physical realities and broader metaphysical principles, fostering a more flexible, comprehensive scientific approach. Conclusion. Critical assessment. Islamic scholars were not passive preservers but active critics who identified and corrected errors in Greek texts, reassessed observational data, addressed theoretical inconsistencies, particularly in Ptolemaic astronomy, focused on classical Greek authors. Debates centered around the works of Ptolemy, Aristotle, and Galen rather than contemporary Byzantine or Sasanian scholars. By engaging with texts already considered outdated, scholars had the advantage of spotting flaws more easily. And this point also shows our point from the first chapter that there was no scientific tradition going on in the Byzantine or Sasanian empires, intellectual and socio-political context. Translated texts were not chosen randomly but served specific purposes, aligning with the debates and reforms of the time. Greek science became a tool in addressing societal and intellectual challenges. Emergence of new disciplines. Fields like Hayat, Islamic astronomy developed to meet the dual demands of religious acceptability and scientific rigor. These disciplines maintained respect for classical knowledge while forging an independent path. Critical spirit beyond astronomy. This critical approach extended to other fields including medicine, where scholars like Abu Bakr al-Razi, Abdul Latif al-Baghdadi, and Ibn al-Nafis emphasized empirical observation over inherited theories. Refinement of mathematics and astronomy. Later scholars like Shamsuddin al-Khafri redefined the role of mathematics as a tool to describe physical phenomena rather than as an end in itself. Influence on modern science. Islamic scholars' engagement with Greek science laid the groundwork for significant advancements. Their active critique, correction, and refinement of Greek traditions directly influenced the development of modern scientific methods and ideas. And that is the end of this chapter. And this chapter was the longest chapter of this book. And in the next chapter, we are going to be talking about Islamic astronomy defines itself, the critical innovations of Islamic astronomers. Stay tuned for that one.